Hola! Alright, so we're going to talk about the saturated, supersaturated, unsaturated part of the solubility curves and how it relates to undissolved solute, and then the interface between the particles that are doing the dissolving, which we always call the particles that are doing the dissolving, solvent that are being dissolved, solute, and they come together to make a solution. Okay, and there is an energy curve associated with this. Remember these reaction coordinates? This is an endothermic, well, actually an exothermic process. It takes this amount of activation energy to achieve the state of no return. So at the transition state there, and only solutions, not only with an asterisk mark, solutions that have a delta H that's negative will actually dissolve. So it must be an exothermic process. Why? Okay, but why exothermic? Why would things that occur, chemical reactions or physical processes, why would they need to be exothermic most likely to occur? Think way back. Okay, I'm going to say this like for the fourth time. Why would a solution, the process of forming a solution, need to be exothermic for it to actually occur? Okay, what do you mean more stable state?
Instead of having a high kinetic energy, it'll release some of the energy.
So give me some. There's some words and maybe variables you might want to talking about. Okay, that's actually, we're not going to call it spontaneous necessarily. We're going to call it thermodynamically favorable. Thermodynamically favorable. What are the two driving forces that say I'm a favorable reaction? But what about entropy, and what about enthalpy, and what about entropy? So positive delta S, which means you're increasing in entropy or in disorder, and negative delta H, which means that you're exothermic. These come together to make what other variable? Negative delta G. Negative delta G is our spontaneous or thermodynamic favorable condition. That's because what's happening to the free energy of the system? To the universe, right? Satisfying what law? Second law of thermodynamics. There you go. So we want the free energy of the system to decrease, the free energy of the universe to increase. Okay, so we're going to get back into thermodynamics a little bit. We have a lab related to it when we get to the solution process. All right, and then this is just a quick review of your IMFs. This is the increasing strength of attraction, and I'm actually going to go like this because this is really, it's been messing with my head recently. This thing, I don't like the way it looks. All right, so the strength of the IMFs, we're mainly going to be talking about ion dipoles this unit because we're talking about the solution process, and a lot of times we're dissolving what kind of things? Ionic compounds, which would make our ions. What kind of things do not make ions in solution? What kind of things don't make ions in solution? Molecules, or so atoms or gases, or insoluble ionic compounds, right? What's something that's insoluble? What are your rules? Okay, so Cash and Gia are your soluble ones. CHOPS are your insoluble ones. What's the CHOP stand for? Carbonates, hydroxides, oxides, phosphates,
And sulfides.
Sulfides. Right, good job. And a lot of the heavy metals are insoluble, and then there's a couple like CBS ones thrown up at the top. All right, so regardless, though, we know our dispersion forces are from induced dipole moments. Those are induced dipole moments. The strength, this is the weakest, then dipole, which is from your polar molecules, then hydrogen bonding, which are from your ones with H and off, and then ion dipoles are actually somewhat stronger than hydrogen bonding because they happen about 6 to 8 times. So ion dipoles have your ion in the middle, which is a full charge, right? Full charges create a higher force of attraction than partial charges. These are all partial charges. So when you're doing your Coulomb's law, force is equal to Q1 times Q2 over distance squared. If Q1 is a partial charge and Q2 is a partial charge, partial positive and partial negative, that force is really not humongous, but it's still significant. But what if you have a full charge? That full charge makes that numerator great. It makes it vastly, vastly larger. So instead of having a partial positive charge, like maybe it's 0.33 positive, that's nothing. If you have a 1 plus charge, that makes a big difference in your force. That's why ionic compounds, NaCl, 1 plus, and then 1 minus, these plus 1 and minus 1, they have a large lattice energy versus the partial charges of all these things that are hydrogen bonded or dipole-dipole. Does that kind of make sense? So ion dipole, I didn't want to tell you that when we were doing daily IMFs, and we're going to go into kind of more IMFs. These partial charges don't really have a significant force. The partial charges with an actual ion do have a significant force. And then this is just another picture. I found some really good pictures this weekend. So dispersion, your hydrocarbons are big there. Dipole-dipole, strong dipole moment there. Ethanol, dash line for your hydrogen bonds, and then your ion dipole. Okay, and then so we just talked about the enthalpy part. It prefers to be exothermic. Do we have any solution processes that are endothermic? Have you ever felt anything cold to the touch when you're dissolving things? NH, NH4, ammonium nitrate, right, is one of our only endothermic processes that's still dissolved. There's a reason behind it. You remember that we had our delta G is equal to delta H minus T delta S? Remember this equation? Okay, for this to be negative, this had to be extremely exothermic, or that entropy had to be really, really large, a very, very positive number. So if I have an endothermic reaction, this delta H is positive, right? Well, how in the world is a delta G going to get negative still? If this delta H is positive, how do I make delta G negative? It's a lot larger, right? So it's going to be minusing a very large number here. So in this case, this is very ordered. Ammonium nitrate, there's a big ammonium molecule or ion and a big nitrate ion. When you separate them, their entropy is much greater than it ever was before. It's huge. So that makes this process actually occur. The solution process actually occurs if the entropy outweighs that bit of enthalpy that was a positive number. So physical states are going to be going towards lower potential energy, which means that they're not going to be pent up in a chemical bond anymore. They're going to their ion state. So a lot of times we'll see this described as solid going to NH4 plus aqueous plus NO3 minus aqueous. So the solid to aqueous states is simply the states that have increasing entropy, but then there's other things like mixing that are not making ions, they're just mixing things together, like making a fruit salad. You got your bananas, cantaloupe, honeydew, separate, put them all together, you got a fruit salad that has a higher amount of disorder, higher amount of entropy. That's what this picture is supposed to say. Sideways, I know, I couldn't fit it the other way. So neon and argon separate, they have their own special sets of entropy. Once you mix them together, this is a spontaneous mixing because there's an increase in positional entropy. It's like just positional disorder. Positional entropy is a good thing to say whenever you're talking about this.
Is stability the same thing as disorder, or like is it unstable if it's disordered, or is it?
It's unstable. It's unstable if it has too much potential energy. So unstable refers to high pent up potential energy within chemical bonds, within systems. More stable means the system as a whole is more stable because they've released all their energy.
So the one on the right would be more stable.
Technically, yeah, because it's released. Well, that one, this one, yeah, but that first example was endothermic, so it's kind of like the outlier of our rules. Yeah. Well, no, it's actually it's like a statistics side of things. It's like, okay, argon in this box has this one argon molecule has the possibility of being in that location, position number 1, position number 2, and so on. But if you open it to a wider area, this one has the possibility of being here, 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 here. It's got more possibilities in its positions. That's why it's called positional entropy, the statistical explanation. And then the spontaneous process of mixing, you can see we've got just water, and then we've got water with sodium chloride. This is a semi-permeable membrane. They will equilibrate until they have equal concentrations everywhere, also known as dynamic equilibrium. I'm thinking biology.
Homeostasis.
Okay, it's homeostasis, but diffusion and osmosis are action here. Okay, they're helping. We're going to do osmosis stuff later. All right, and then some of this you already know, because we have all seen my polar bear video like 100 times. But you know, like dissolves like, that means that our solute and our solvent should be the same polarity or have the same IMFs, right? Okay, so the solubility depends on these two things though. One, like dissolves like, so same IMFs or same polarity / IMFs. Or they, what's the word miscible mean? I see your hands going like this.
Mixable.
Okay, mixable. They will become mixed with one another. Miscible liquids always dissolve in each other. That's just because like dissolves like, polar dissolves polar. And then things, so this is just a couple extra helpful groups. What's this group right here look like? So this is an OH group, a hydroxyl group. What's this one look like? C, double bonded O, H. What's the name of that? It's actually, that's an aldehyde. It's called a carboxyl group. Okay, this is another carboxyl group. This is the aldehyde. This is the ketone. Ketones are in the middle. They don't have H's on either sides. This is a carboxylic acid, and that's an amine group, or amide, amide. Okay, so anything that has those on it will be polar, at least on that one end. If it's a humongous hydrocarbon like sugar, C12H22O11, I think is what sugar is, sucrose. They have a couple of OH groups or just O double bonded O groups. So they still have polar areas, but they also have nonpolar areas. So remember, those big biomolecules or macromolecules have lots of areas with different IMFs in action. Nonpolar things will have mainly just C's and H's, hydrocarbons, and they will only dissolve in nonpolar solvents like, what's a liquid solvent that we've learned about that has a cyclic ring? Benzene. They'll dissolve in C6H6, benzene. And this is what that last bullet says. Many molecules have hydrophilic and hydrophobic ends, so they've got the ability to dissolve. Like part of their molecule will be attracted to water, and part of their molecule will be attracted to something nonpolar. So they've got the ability to be slightly dissolved in two different solvents. Sometimes it's a competition, like who's ever washed dishes? Okay, like fatty things, you have to wash. You can't just wash them down with water. What do you have to add? Why soap? It's a surfactant, and it does what?
Attracts both.
Okay, it attracts both. So it's got a hydrophilic and a hydrophobic end. And so what it does is, so if I'm soap, I hold on to water with one end, and I hold on to the oil droplet with another end, and I make them come close together. They're not touching, but I make them come close together and wash down the drain. So that's what a surfactant is. I have a picture of that in just a second. And we pretty much just went through that. These are the three different types of solutions we're going to talk about today: gases, liquids, and solids. The gas solubility is mainly just telling you that gases will dissolve in gases. It means they'll make a mixture. We're breathing in a mixture right now. What's it made of?
Air.
No, okay, not air. Oxygen and nitrogen, carbon dioxide, argon. Okay, it's got a little bit of argon. And water vapor. So all those gases have their own mixture, but a lot of times we have a difference in gas mixtures if one is really, really dense. Because if one is really, really dense, so molar mass is really great, then we've got, a box of air, but the dense ones will sink down, and the less dense ones will stay up here. And when you guys read about the Lake Nyagos, which is in Reading Guide 5, you'll see an example of that. So a lot of times they do mix together, no problem at all, unless their densities are vastly different. Liquids usually will dissolve in one another, but you're mainly what you're looking at for the like dissolves like criteria. You're looking at molecular polarity, and then the solids. It depends on if ions can attract ions. So you know how you can make coordination compounds. That's not just one ion and another ion. There's lots of molecules and some other portions that are included. So solids can make their own mixtures too. Depends on their ability to attract other ions. And then alloys. We talked about alloys, or the two types of alloys. Two types of alloys. Not examples of alloys, types, categories. Here's one. I'll keep going. It's between interstitial alloy, and then the other one where I'm substituting a blank one in for a red one. Substitutional alloys. Those can be solid state mixtures. Alright, last bit here. I always have to show you this cute picture. And then when you get to geology, if you take geology or earth science in college, then you'll get to do a lot more mineral mixtures, which is how we get different variations of diamonds, black diamonds, pink diamonds, yellow diamonds, all those diamonds, because they have impurities within. And then like feldspars, alkali feldspars have potassium and sodium in them. I'll get that in a second. Okay, and then this is the soap part. We just basically talked about it, but the emulsifying agent is the other word I haven't said yet. So they have two portions on the soap molecule. I'm actually going to scroll down to the bottom first to show you what it looks like. Oh, here we go. So here's a soap molecule. It's got this big hydrocarbon chain. You know what this means, right?
Yeah.
What's this corner?
C.
A C.
C.
So there's C's all the way, and then what's around each C? Two H's here, three H's here, and so on, right? So this is the hydrocarbon chain, and then this is it's got a phosphate group in it. It's got a couple of other things too, but it's the hydrophilic area because it likes water. This does not like water. So which end attracts to the water? This part, and then this part is going to attract to the lipid, or the fatty part of like when you're washing dishes. This is what it looks like actually. It does have usually an alkali ion on it. And then what they do is they surround it, they like gang up on the oil particle. Like, you're coming with us. And then they go around it, and then this is called a micelle. The water particles are out on the outside. So it's like layers and layers of stuff around the oil droplets. So I mean, they're pretty darn complicated. That's called what did I just call it? Micelle. It's not my cell, it's just my cell. Guys, I'm fine. Okay, and then that's the basics of it. It's called a surfactant, and then when things actually are surfactants, they pull in polar and nonpolar pieces, they emulsify. They're called emulsifying agents. So it's just another word for surfactant, but it's just going to also tell you that it can make an emulsion. It can make an emulsion. Like mayonnaise is an emulsion. Let's put some emulsion on my sandwich today. I don't like emulsions. I do like mustard, but that's not emulsion. It's just a component of making emulsions. So a lot of like vocab and explanations of solutions, but then we're going to get into concentration units because we haven't done molarity like forever. We're going to get back into math because I know you all miss it. I miss it because I haven't picked up my calculator in like a month. Okay, you guys can see that, okay? So there's 3 steps in the solution process. The solution process is going to require us to break forces and bonds and to make forces and or bonds. First step includes taking the solvent particles, and actually I'm not going to change this to solute. I like to talk about the solute first and then the solvent second. So the solute is going to require us to actually tear it apart. There's no forces there. These are literally bonds. So like if I'm taking sodium phosphate and I need to break it apart, I'm going to break it into 3 sodium ions and 1 phosphate ion. And if this is, let's just call it solid, aqueous, this is going to take some work. Okay, that is not a process that just naturally happens. It's endothermic. It requires me to pull it apart because what's holding it together? Lattice energy, right. This is usually equivalent to some lattice energy, which is a huge number in most cases. Then the second thing I have to do, so the reason I have to separate the solute is because I need to be able to mix it within something else, which is my solvent. So then I need to break the solvent particles apart. But what's holding solvent particles together? IMF. So for example, water, I need to take my water, I'm going to say times infinity, I don't know how many there are, and I need to break them into water and water, etc. I need to separate them. I'm not separating bonds, I'm separating forces, I'm overcoming forces. So which do you think usually takes more energy? It depends on how much you have, but usually the first one, this one can be really large as well, it depends on how much you're mixing. So this is you're overcoming hydrogen bonds or IMFs here, or whatever you're coming. If you give it a non-polar solvent, what are you probably overcoming? What force? Line dispersion, right. So endo. Last one is the actual mixing part, where the solute says, hey, solvent, let's get together. And they actually attract to one another. Because a solvent, water, has a hydrogen bond or a dipole moment on it. So, oh, so cool. I'm not sure what's happening. Let me see here. Okay, right. So it has a dipole moment on it. If it sees a sodium ion or the phosphate ion, it's going to surround it with the area that's attracted to the sodium. So what part of water is going to be attracted to the sodium? The oxygen. What part is going to be attracted to the phosphate? Hydrogen, because that's the positive end, that's the negative end. So we need that to happen, and that's actually a happy process. That's a process that will occur naturally. It's exothermic. That's energy stabilizing. So here's a picture to represent that. Step 1, expand the solute, separate the bonds. Step 2, separate the solvent, overcome the IMFs. Step 3, come together as a solution. Okay, so we're going to talk about what each one of these means. The first one I always call H1, H2, and then H3. H1 is representing what? The solute, H2, solvent, H3, process, right? Solution process. All right, and then, so this is just an example of that. You can see, like, I don't have to label pictures for you to know what this is. What is the blue part of this? The oxygen. And then H is going to be the kind of like dark colored part there. So if this was a solute, oh crap, it says right there, anions. If that was an ion, it would have to be the anion. And so forth. Cations are going to be the smaller ones. You remember, cations lose their valence shell, become smaller. Lots of review here. Okay. And then ion dipole attractions are strong. So that's actually very, very, very stabilizing. Energy is released when this happens, when the new IMFs take place. All right, and then let's fill in the blank here. This elevation process occurs with ionic compounds is superbly energy lowering because the electrostatic attraction between ions and partial charges of water. Most of the time, there's 6 of them that surround it because of lattice. Let's look at this one in the middle. This gray one in the middle. It's got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Usually it's 6 ions around it. This is not a good lattice, but it has 6 ions that can surround it. So what is the IMF there? Between this, read my sentence. What is the IMF called? When ions and partial charges on water attract. Ion dipole. Okay. And then last one here. Oh crap, okay. So the process here of H3, which is the solution process, the mixing process, that has to be greater than the combination between H1 and H2. If not, the process usually won't be exothermic enough for it to occur. So if our solution, if H3 is greater than the sum of H1 plus H2, then overall delta H of solution is negative. That is much preferred. If it's not, that means it's endothermic. And so what has to outweigh the enthalpy for this process to occur? Entropy. Right. That's what that says. The entropy will overcome the endothermic nature of it. We just talked about that though. All right, and then we went over that. There's one more word we're going to talk about. It's the heat of hydration or enthalpy of hydration. What does it mean to be hydrated? Maybe you got a lot of water, so hydrated here means you're going to be surrounded by water molecules. Some of this is redundant. I'm quite sorry. Are we okay with the first part? Negative overall. Okay. Value of H3 must be greater than the sum. This also, the process we all know ionizing usually is entropy is increasing. So why do solutions form? When this overall entropy and enthalpy are causing a thermodynamic stable or thermodynamically favorable condition. This is not the part I want to show you. This is the next part. Okay, energy of hydration. Enthalpy of hydration is the sum of two things, H2 and H3. What's H2? What does it represent? Solvent breaking part in H3. The solution attractions. Those attractions are called what again? Most likely? Ion dipoles, thank you. Because most of the time we're talking about salts being dissolved here. And a lot of times we're doing hydration, which means water. So it's probably going to be a salt, which will be ionizing, and then water molecules coming together. So if I take this and this and I pull it together, I can call it H2. But a lot of times what I can do here is lattice energy we can't measure, we have to calculate. That's what we did that Born-Haber process where we went through and calculated lattice energy. This is the second way to calculate lattice energy. Because lattice energy, if it's an ion or if it's an ionic compound, will be equal to H1. So if you know what the H2 and H3 are, and you know the delta H of solution, which is the sum of all these, how do you get to H1? Yeah, subtract. So take what you have from H solution minus H of hydration, and that will give you the H of the lattice energy, which is strictly the lattice energy, which will be in kilojoules per mole. Okay, so we have another way to calculate lattice energy, so that's pretty much what I showed you here. So that's H of hydration is just representing the part, not the lattice energy part, but everything else. And then there's like a definition here for you. It's going to allow you to combine the solvent and the solute interactions, and a lot of times it talks about it in terms of gaseous solute. Because remember the definition of lattice energy? What is it? Two gaseous ions, right. So when Na plus gas and Cl minus gas come together, they make a solid sodium chloride. So the definition of lattice energy is including gaseous particles. So the enthalpy of hydration is also including gaseous particles. Because remember, solid ion or a solid ion and another solid ion, they don't move. They don't get together. They have to be mobile. They have to have enough kinetic energy to collide and create something new. And that's why these have to be gaseous. And a lot of times this enthalpy of hydration is a negative value because of what? What's H3 usually? Exothermic. H2 is usually endothermic, but H3 should outweigh H2 because that's the energy delivery process when they're mixing together. And then I kind of just told you this, but I'm going to show you anyway. Okay, so this is how you kind of sometimes call it versus the lattice energy, since it's the part where, so lattice energy is energy released when two ions come together. This is kind of talking about the opposite way of it, so we're going to call it crystallization. So it's still lattice energy, it's just the positive version of it, but you can calculate that. Crystallization is just the opposite. Same formula we just talked about there. This is going to be the hydration there, which is usually a negative value. H of solution is usually a negative value. This is usually a positive value because you're talking about the endothermic. Well, no, it can be negative too. Lattice energy is usually the energy released. So this can be positive when gaseous ions come together. Thank you for bearing with me. Lots of terminology here. You okay? Go forward? Okay. I'm missing Brienne and Adia and And then this is the same thing. I'm going to skip this for now. This was just extra stuff from the textbook. PowerPoints, they have very wordy stuff, but it's good for studying. It's online already, so you can look through that. I think we already mentioned everything we need there, though. Yeah, we'll get there. Okay, so your different types of mixtures, aka solutions, can be solid, liquid. We just talked about that. That's our aqueous version of it. I just don't want you to only think of mixtures or solutions as aqueous. There are multiple other types. Solid, solid, what was my example earlier? Thank you. Alloys. Liquid, liquid. Give me an example. Anybody? Think of one. Huh? But that won't be a liquid, so that'd be brass will be our alloy. I'm sorry, no. Give me a liquid, liquid. Sorry. Gas, gas. We all know is the what? The atmosphere, right? Give me one of liquid gas. Soda. Okay. Liquid, liquid.
Smoothie.
Oh, you could say milk. I can go with that. Smoothie. There's probably some solid particulates in there. I was gonna. There's lots. There's actually quite a few. Food coloring in water.
Mio.
Neo. Yeah. And then remember, a solution is a homogeneous, however you want to say it, mixture. They're uniformly mixed throughout. So if I ever say solution, you should be thinking homogeneous. So those are all the different types. On a multiple choice question, do not get that wrong. It's like which of these is not a mixture or something like that. All right, you're almost there. And then you guys know your like ethanol solutions by the store. It's like 50% ethanol. That's a liquid as well. That's what I was thinking about here. Like 70% isopropyl alcohol or 50% ethanol or whatever it is, like cleaning agents. Or hydrogen peroxide, 3% hydrogen peroxide. That's got water in it. Yeah.
Put that in our ears. Like,
I think it bubbles up and there's like nucleation sites and it bubbles up and brings out whatever you're trying to get out. Bubbles that make it listen. Your teeth are supposed to get stains off. I would put hydrogen peroxide in my mouth. I would. That's me. All right. These, you know the solubility curves, yes? This is always in grams of solute per 100 grams of water, which is usually our solvent, though. Okay? So this is not per solution. This is per solvent. That's just a common unit that you need to be very aware of. What do you notice about the difference between solid curves and gaseous curves? Say it again.
The colder gas, the more easily it'll lose its form.
Okay, so give me explanations to why that works for gases.
They'll be able to particle the molecule. Okay. The particles can slow down more so that they can enter the water.
Lower kinetic energy means less vaporization, right? So less vaporization means where the gas particles stay in the solution or in that solvent, which increases their concentration, right? So solubility is in grams of solute per 100 grams of water. It's the same thing here for gases. It's just written as a concentration unit. So methane, which is really, really lightweight, CH4, versus, well, this one's really lightweight too, versus oxygen. Oxygen, you can usually get more in there than methane. Why? What do you think? Actually, this is less in there. That's solubility. That one looks... That doesn't make sense. We'll go with it, but it doesn't make sense because surely oxygen should, since it has a higher molar mass, should become more involved with the water molecules and it's polar. But you know, graphs and stuff. Okay, so otherwise, increasing temperature should increase the concentration. or increasing solubility of solids, and vice versa for gases. So that's what this says right here. For a solid state, solubility increases with increasing temperatures. For gases, solubility decreases with increasing temperatures. And it's all based on the kinetic energy that gaseous molecules have. If the gaseous molecules have enough kinetic energy, they can overcome their IMFs with the solution. If they overcome their IMFs with the solution, they vaporize. Have I gone through this example yet with soup? Okay, what's the first thing you do when you're trying to eat soup? Okay, I do not put ice in my soup.
Okay.
Okay, it's been cooked, been delivered to you out Panera. Okay, why do you blow on it?
Rubens, you're not the only one that put ice in my soup.
Why do you blow on your soup spoon, guys? What do you
It
mean?
doesn't burn your mouth.
But why is it cooling down when you blow on it?
Because you're reducing the kinetic energy.
How?
Your breath is colder than the steam.
Stop the steam.
No. Okay, what do you mean stop the steam? What do you mean lower the temperature? Give me more. Definition of kinetic energy, or temperature. Let's do a definition of temperature.
Kinetic energy.
Presence of steam.
The what? It's not just kinetic energy. Average kinetic energy. So if temperature, this is for the benefit of my viewers at home, temperature is the average kinetic energy, how does blowing on a soup spoon decrease the temperature? Go for it, guys. Come on.
Blow like a relief kinetic energy because they're like vapor.
There's my soup spoon. Okay, so there's particles coming off the top. Those particles have what? They're vapors, but they have what? Extremely high kinetic energy, right? They have so much kinetic energy. They are removing themselves from the liquid stage. The liquid stage, which has lower kinetic energy, you know, from solid, liquid to gas, we've increased kinetic energy because they have more energy of motion. If you blow away the high kinetic energy ones, what's left? The low kinetic energy ones, which relates to lower temperatures. So what are you doing? You're blowing high kinetic energy particles away from your environment to cool it down. The lack of kinetic energy relates to lack of temperature. Kind of cool? Okay, so what you're doing is you're lowering the average kinetic energy because you're taking the highest kinetic energy particles out of the system. Yeah.
What's with sodium sulfate?
Sodium sulfate is weird. The sulfate particle interacts with solute very well because it's the high attraction, the 2- charge. So it kind of like interacts a lot, but it doesn't increase. I can't explain these. They're all based on ion dipoles and stuff like that too.
Alright.
Okay, and then I didn't actually go through this. On these curves, we're supersaturated. Alright, so if I'm talking about this line for sugar, supersaturated is here. What's this part? Saturated, below, unsaturated. Definition of saturated?
Definition of what?
Saturated.
Ratios.
No, there's nothing about ratios necessarily. Huh? Dynamic equilibrium is what?
Precipitation.
Not solute and solvent. Okay, solvation, which is the dynamic equilibrium between undissolved solute and dissolved solute. Okay, so this is when you have an equilibrium between undissolved solute and solvated solute, and then supersaturated is when you have too much solute per solvent at a specific temperature. So this can be supersaturated at 40 degrees here, but if I have that same amount at 50 degrees, it's saturated. It's all temperature dependent. This is very, very, temperature controls a lot here. And then unsaturated means you can dissolve more in there. You have not met the saturation point. You can continually dissolve more solute per solvent at that temperature. What happens if you disturb a supersaturated solution? What's that name? What's the word for that?
Crystal.
Okay, it does crystallize, but there's another word for that. It's called desolvate or desaturate. What's your question, Michael?
Will we have to be able to determine the saturation point?
It would even be given to you in a graph unless it was given to you as enough information for you to calculate that for. Okay, make sure I told you everything here. Yeah, okay. Alright, and we talk about rate of dissolving a lot, and I don't want you to think that if you continually stir something, it's just going to keep dissolving. We know that there's a max saturation point for all solutions, yes? Like I can keep putting sugar in my coffee, but eventually the sugar's going to topple out of my coffee. It's not going to be dissolving all the time. But all you're doing is when you add these factors in or affect the solutions, you're increasing the rate at which they dissolve, not the amount. Cool? So two things that we talk about a lot is surface area. So a block of sugar does not dissolve as fast as powdered sugar, and the stirring or agitating. I think I have agitation. Yeah, stirring and agitation in the surface area, but not the amount. It's only increasing the pace at which it dissolves. That's common sense, I think, but a lot of times you're like, yeah, just keep stirring. It's going to keep dissolving. Yeah. Right? You guys laugh. Okay, these are the last bit. This is the concentration reminders. You know that molarity is moles of solute per liter solution. Molality, actually, in a second. So write down what you need to here. You're going to be doing some concentration calculations tonight, so if you don't have the units, it's going to be hard to calculate. Just want to make sure we remember this stuff, so I'll be quiet for a minute. Okay, right now. I might just make this one bigger. I'm sure you guys remember most of this, but I have one example I'm going to repeat for all of them. Alright, so molarity, molar, big M, moles solute per liter solution. And now, since we're doing solutions, we're going to be talking about each of the components. I really, really encourage you to write, moles of solute, whatever it is, over this moles or liters of solution, or whatever it is for mass percent, etc. I don't want you to think you're writing moles of solution, for example, and then get the question wrong because you just neglected to write the full unit. So units are back in the game here. Percent by mass is just mass of solute over mass of total solution. So a lot of times you're not given total solution, so make sure you sum the solute plus, so I'm going to just give it sol, but we don't know what that is. So solute plus solvent. Don't forget to make the total solution for the bottom there. Mole fractions are represented by x of whatever, xa. And that's always moles of the thing of interest, which is usually the solute. Not all the time. This substance could be solute or solvent. And this is the total mixture, so make sure you don't forget to sum there. Molality. Let's scroll down. Oh. This thing is real funky, guys. I apologize. I have to be going like this. It's being weird and stuff. Oh, I didn't read the picture of this. The molarity is affected by temperature. Why? Because it contains what unit? What unit would be changing with temperature? Liters, volume. Volume changes with temperature because what happens when you increase temperature on something that's a liquid solution a lot of times? Huh? Okay, it expands. It's called thermal expansion. Thermal expansion. anything with volume can have that effect whenever you increase the temperature, or condense whenever it is cooled. Does mass change with temperature? No, just volume does. That's the only thing that's going to be able to expand, 'cause it's got interparticle spaces. Solutes that are solid usually don't. So that's why the volume is only listed for molarity up there. And then down here, molality, little m, is moles of solute per kilogram solvent. That's related to mass. That is mass, so it does not change with temperature. And then last one is normality. Normality is just labeled with a big N, and a lot of times you'll see that with acids and bases, and it's related to the moles of X created, whatever we're talking about. So, for example, HCl, 1 molar HCl is 1 normal HCl, but 1 molar sulfuric acid creates double the H+, and so it's called 2 normal sulfuric, because it creates double of the particle, which is usually the acidic portion. So sometimes on light bottles you'll see 2N, and that's equal to 1 molar. So I always convert back to molar, because that's what we know how to use most likely. Next, I'm going to talk about mole fraction real fast and density, because we did mole fractions really, really briefly in honors, but it's a fairly new topic. Okay, so we're going to use this a lot with vapor pressure, which is we're starting tomorrow, like in-depth vapor pressure. So make sure you know it's moles of things that you want over the total moles. So you always have to get moles and add them together. It's unitless, yay. And then you always represent it, even though it says fraction, you always represent it as a decimal. So if you have 0.5 moles of something over 1.0 moles total, you don't say 1/2, you say 0.5. And that's it, no unit. You always represent it as a decimal, just because that's the common way of expressing it. And then the last slide, I didn't say this. Occasionally you'll see the words like solvent, or no, it'll say volumes or additive. If the volumes are additive, then make sure that you actually add the volumes together. If it says so in the problem, that's a word that's a phrase that's commonly used. Or it'll say volume of solute is negligible, and so you just ignore it. That's also a phrase, so that way. So don't forget to actually read the question when you're going through these types of problems, because if not, you'll have like the wrong amount of solvent or solute. All right, and then this is the chart that's in your book. The only thing I just want to mention is that there are a couple ones that we're not going to use as often, but they are there. The mass percent in parts per million or parts per billion. Million is 10 zeros. I mean, not 10 zeros, 6 zeros away from your normal state. And then parts per billion is a multiplication factor of 10 to the 9th. It's hard to see because it's in blue. Billion is, this thing. So a lot of times you'll give the number and you'll say times 10 to the 9th. That's all. I'll show you it down here in just a second. But those are ppb or ppm, parts per million, parts per billion. So you guys remember when West Virginia couldn't drink their water like a month ago? No?
Yep.
Get out some more people. So my sister lives up there, and she was like, I have to go to Sam's Club and buy like 100 bottles of water because we can't drink our water, we can't shower with our water, we can't make coffee, can't do nothing. Because of the coal. There's a coal manufacturing plant there that leaked chemical, it's some sort of organic substance, into the water, and it was like they had to wait for it to get below 1 part per billion before it was drinkable. That's crazy small. You could have 1 milliliter of solute per billion milliliters of solvent or solution. It's crazy low. So they couldn't drink anything for about a week and a half, I think. She came down here and got water because they were sold out. It was a hot commodity up in West Virginia. So it was serious. And then it flows into all the other river basins and, down to us. So we had to, monitor our water supply as well. Okay, so parts of solute for every million parts of solution. And then so here's an example, 36 parts per million by volume, and there's 36 milliliters of solute and 1 million milliliters of the solution. So this is just making sure you know what PBB means, or PBM, whatever it is. Alrighty. That's a good example if you just can't remember. If you just want to know the basics of it, write down an example. 36 parts per million is 36 milliliters of solute over 1 million milliliters of solution. And then anything with volume in it is temperature dependent, so this is temperature dependent. Yes, yes? Yes, yes, thank you. I'm sorry, today's kind of a fact-filled, exciting day, but this works with me. I'm trying to keep, I put the picture of the group leaders up there, guys. I don't do that for just anybody. Okay, let's do this problem together. A solution is prepared by dissolving 25 grams of magnesium chloride in enough water to make 450 ml solution. Calculate the molarity, so that's part 1. And a solution is prepared by mixing 85 grams of hexane and 45 grams of decane. Calculate the molarity, molality, mole fraction, and mass fraction. Let's do the first part. What do you want to do? So go for it.
25 times.
In your head. What is it? 95.2. 1 mole of magnesium chloride. 95.21 grams of magnesium chloride. Alright, and that gives us 0.263 moles. Okay. What else do we need? Right, so this divided by our what?
Times or divide 450 milliliters by 1,000. So to get that to liter.
What is it?
0.45.
Thanks. 0.45. I'm gonna put decimal there, so we have 3 sig figs. Liters of solution, and that's only because this said enough water to make a 450 ml solution. It doesn't tell you how much water you took. If it did tell you how much water you took, that would be, if it said it took 450 mils of solvent, then what would you have to do before you'd have to add volume? So how do you get the volume of something like this? What value would you need? Density. You would say, Miss Emily, what's the density, which is mass per volume, of that specific substance? Or I might say that 25 grams is negligible in its volume, and so we would assume the solvent equates for 99.9% of the solution. So I know there's always different words. Solution, so then we would just ignore the fact that that was in there. But if I didn't tell you it was negligible, you'd have to add. So this divided by this will give us our molarity to be 0.584 molar magnesium chloride, and there are 3 sig figs there. Alright, let's do the last one. So a solution is prepared by mixing 85 grams of hexane, that much decane, molality, mole fraction, and mass fraction. What do we need for molality? Moles. Okay, so what's the solute? I don't know. It doesn't say, but what is the general purpose of having a solvent? What's its job?
To dissolve the solute.
Which is usually in what magnitude difference? You usually have more solvent than solute. That's generally how solutions work. Because if not, if you have too much solute, it's not going to dissolve. So who's the solute? Decane. So formula for decane?
C10H22.
Okay, so moles of decane, because that's our smaller number. This is our solute divided by what? Which is formula C6H14. You're just doing 2n plus 2 in your head. Yes? Okay. So now, molality. I've got 85 and 45. What am I starting with? 45 grams of decane times a molar mass do in your head? Huh? 142. I think that's what I got to. Yeah. 1 mole decane. 142 grams of decane gives me 0.317 moles of decane. So I need that for the numerator, right? And then kilograms, what do we need to do? So can you do that in your head? Right, so what's the kilograms of hexane? Yeah, you're just moving that 0.85 back 3, 0.085 kilograms of C6H14, and that gives me a molality of 3.73 molal C10H22. I'd like for you to label what you're talking about, just because it makes it a little bit easier to find answers whenever I'm looking through all your work. That'll just for you there. All right, so what was the next thing you defined? Mole fraction? Mole fraction of decane. How do I do this? Give me the formula, like the setup first, then we'll go and calculate. Okay, so most moles total. Alright, so that's going to give us the X, which symbolizes mole fraction of decane. Alright, do I have moles of decane? Right, I do. It's right there. 0.317 moles of C10H22 over, what do I need to do?
Molar mass of hexane.
Alright, so I need molar mass of hexane. I need 85.0 grams of hexane. What's the molar mass? Keep doing it in your head. 86. Good job. Just practicing that mental math. 1 mole of hexane is 86. That's about 1 mole. You can see from the top here. 1 gram of hexane is 0.988 moles of hexane. So what am I doing now? Great, so 0.317 plus 0.998 moles total on bottom, and what's that number equal? 1.315, but what's the fraction?
Oh, do you want?
Yeah. Answer, sorry. 0.243, I think, with our sig figs. So notice we're putting as a decimal, even though it's called a fraction. Words that don't mean words. All right, part D was to find the mass fraction, I think is what it said. Mass fraction of hexane. So go for it. Same thing as mass percent, except we're not going to times it by 100. It's just a fraction. Mass. How do you want me to start it?
Hexane.
Mass of hexane, which was 85. C6H14 over everything, so 85 plus 45. No timesing by 100, because we're not doing mass percent, we're doing mass fraction. If it was mass percent, then you just take this and multiply by 100. So that should be 0.645. If it was mass percent, it would be what? Yeah, 65.40. Alrighty, quick review of that. Thank you for those of you who are bearing with me, because I know some of you guys remember this really well. It's just math, making sure you have your own concentration. Oh, I'll do that in a second. I'll do it for you. You have your own concentration, day 1 concentration, or process 5 on here. So you guys can start this now. About 30 minutes. I know you can get that done. And if you want, or just for fun, if you want to do a challenge tomorrow with who can make the best soda geyser, the largest, the tallest soda geyser, you can for more money. Bring in your own stuff because you got to design how you're going to do it. I'm not going to tell you it's a Diet Coke or regular Coke or Mountain Dew or whatever works the best. If you want to, you can do it with a partner and challenge each other for more money. So that means we have to go outside tomorrow. Darn it. Is it? Oh. No, I think it was supposed to snow this morning.
Actually, it's gonna start clearing up tomorrow.
I think it is. Yeah.
It's supposed to get us about 7.
Yeah. So if you would like, that's an option for mom money.
Let's do it.
It's totally up to you. If you want to, that's cool. If you don't want to, that's also cool. I'm going to stop recording now.